Hey there, welcome to this video about retrieval-augmented generation. Here we'll cover the underlying concepts behind RAG and then explain how we can build a very simple implementation of it and then move into a more sophisticated way of implementing it using a vector database called Chroma. So if you don't know what RAG is, or if you're trying to learn how to implement it in practice, you're in the right place. So as the name suggests, retrieval-augmented generation is a technique that enhances the output of large language models by adding a retrieval phase before trying to generate. So language models are limited to a knowledge cutoff, and also they're limited on the training data that they were trained on. That means that no LLM in the world will have internal information about your company, for instance, or about your personal life, or about updated real-time market data, for instance. All of these scenarios are things where we would need a retrieval phase to fetch that information and pass that into the prompt of the LLM so that it gets enhanced with that context, right? So RAG is basically any system that does retrieval through an API or any other database or some other system, some external source, and then enhances the LLM's outputs using this context. So this means that basically every AI app or product that you use is in some shape or form RAG, right? So for instance, when you go to ChatGPT and then you enable this web search function, this will enable it to browse the web first. That means retrieval. Then it will use these sources from the internet to enhance, to augment the generation that it will output, right? So that's retrieval-augmented generation. Another example would be a tool like Vecto, which has context about my short-term and long-term goals and about what I do professionally. So if I tell it to write a poem about me, it will first retrieve the context that it has about me and then use that to augment the generation, the output of the LLM with that information that it gathered. So like I said, pretty much every AI app or product that you use uses RAG in some way. So that being said, the most common implementation of RAG is using a vector database. Vector databases are database systems that can store documents or chunks of text in a high dimensional space. And where in this high dimensional space the documents will get stored at will depend on the semantic meaning of that document or of the words in that document. So what this means is that documents that are related in meaning, so documents that are about the same thing, will get stored closer together, right? So you'll have groups of documents that are stored close to each other based on the meaning and not just the keyword matching or the syllables. So this way, when you have a user query, the only thing we'd have to do is embed it as well in this high dimensional space and see where it's located and see which documents are closer to this user query, right? So we can get by distance the most related documents that are actually relevant to that user query. And this is so much more efficient than just keyword matching, which is what makes vector databases so OP. That's why it's the most common implementation of the retrieval phase for RAG, right? This is the state of the art for matching documents or knowledge base articles to a user query. So now that you have a basic grasp of the concepts of RAG, we can build our first version of a RAG application. For this one, I'll keep it very simple. I'll just make the retrieval phase a simple word search on a list. So we'll have a hard-coded array of documents and then we'll search them before enhancing the LLM output with this. This is just so we can grasp the phases of retrieval and augmentation. So let's first install OpenAI and Python.env. Okay, I'm using OpenAI for this example, but you can use any LLM that you want, that you prefer. I'll just use GPT-4o mini because it's pretty cheap and the SDK is very easy to use. So let's first create a .env file. Here you should put your OpenAI API key. So then we can create a new simple rag.py file. So here let's import OpenAI, OS, and load.env, and let's also call the load.env to load our API key here. So then let's create a class for our rag. I think this will make it more organized. Then we can define an OpenAI client and pass our API key to it. Here we won't be using any vector database, so we don't need any embedding function. Let's just create simple def called retrieve documents, and then we can pass in a query and to do implement document retrieval, and then we can have a generate response method as well, which will try to retrieve any documents and then call our OpenAI client passing anything that it finds. So, okay, let's also define documents, which will be a list of strings, and we can set that variable in our class. So first, let's normalize our query, just make it lowercase. And let's also remove anything that's not a word or a space character. Let's replace that with nothing. We also need to import regex here. So this will take off any commas or punctuation, anything that's not a word or a space. This will leave just the words and the spaces in our initial query. Then we can create a set out of the words in our query. So this will split by space, and each word in our query will become an item in this set. Then you can have matching documents that initializes an empty array, and we can loop for each document in our documents list. This is good, but not exactly what I want to do. So I can do normalized documents equals, yep, this. All right, so we're doing the same thing, getting just words and spaces from the lowercase version of our document for each document. And then we're splitting all of that, all of the words in this document into a set. So now we're just trying to find the documents that have any of the words in our query. So this is the shittiest implementation of a search function that we can have, but this is just for an example of how to implement this RAG. So now let's move to the generate response method, where we'll augment our user query with any matching documents that we find using this other method, right? So I'll add this underscore just to indicate that this is an internal method. So here we can find relevant documents equals self.retrieve documents query. Okay, this is perfect. Then we can create a prompt. Here in the prompt, we can say like, please answer the following question based on the following documents. And then we can show the documents, and then the question will be the query, and our response will be a call to our OpenAI client. So very simple stuff. We're getting the first choice of the LLM response, and we're getting the message and content from that response. So quick recap of what we're doing here. We're first retrieving the relevant documents based on if there's any word in our query that is also in the document. And then we are creating a prompt that includes the documents that we found that match our query and our query. And then we're just passing that prompt to OpenAI to get a response there. All right, simple enough. So we can now instantiate our RAG. And here in the documents, we need to pass the actual content of each of the documents that we want. Okay, so I just added 4 documents. 2 are about RAG and vector databases. One is about my dog being a good boy, and one is about Vector being the best AI productivity app in the world. So now we can query our RAG. So print generate response. So I can ask, what are vector databases and how do they relate to RAG? So to add some visibility of what's happening behind the scenes, let's actually print here the retrieved documents, right? Let's print the relevant documents. Let's add some line breaks here to make it easier to read. Then let's call our simple rag file, Python simple rag.py. Okay, I don't know what this error means. Let's ask cursor. Ah, right. Okay, so I need to name the parameter. So this is API key equals last.getInf OpenAI API key. Okay, let's run this again. So it retrieved 2 documents, right? The 2 that are related to our user query. So it got the document about RAG and the document about vector databases. And then it used those, passed those in the prompt for the LLM, and then generated an output that was built on top of that context that we used to enhance this. So congratulations, you've built your first RAG application. Now let's move into a more sophisticated example with a real vector database and an embedding model that we can use to index our documents into this vector database. All right, so for this more complex RAG implementation, we'll need to install some more Python packages. So do pip install Pydantic. I'll be using Langchain because we don't need to reinvent the wheel here, right? With Langchain already has lots of good integrations with both embedding models and with vector storages. So that's why we will also install the optional packages Langchain OpenAI for the OpenAI embeddings and Langchain community for the vector store integrations. I'm especially interested in the Chroma vector database, which is a very simple to use that has a really good Python SDK that we can leverage to build our RAG. Okay, now that we have installed that, let's create a new file, advanced rag.py. And here let's import os openai.env. Let's create a new class, advanced rag, initialize it. But here we won't be passing documents like this. I'll actually use a better more sophisticated approach here for this one. What I want to do is create a docs folder. And in this docs folder, I'll create some markdown files and we'll use those, we'll get those from the file system and index those into Chroma database. And then on the retrieval phase, we'll query ChromaDB to actually enhance our response. This means that we will need to have another step here, which we didn't have on our simple implementation because we were not using vector databases, which is embedding. Let's call this one load documents. So lang chain documents. Let's start with an empty array. All right, let's first also import some important stuff. First, let's import our OpenAI embedder from langchain OpenAI port. OpenAI embeddings. From LangChain core, let's also import this document. Actually, langchain.schema is the correct package name. From langchain.text splitter, let's import this recursive character text splitter. We also have another simpler text splitter here, but this is a very common and useful one to use. From langchain community.vector stars, let's import Chroma. From Pydantic, let's import base model and field. This will be used for our structured output. When calling the OpenAI API, I'll require it to provide us the answer, some reasoning, and the sources. So it will have to cite the documents that it used to generate our response. Let's also import JSON and import glob. Glob will be used to find all documents that match a specific wildcard pattern, and that's what we'll implement right now. So here we can loop for every file in glob.glob, and then we'll find everything inside the docs folder. That's a markdown file. Then let's open each of these documents. Let's also strip this to remove any white spaces from the beginning and end of the file. Okay, so let's also make the source name here the name of the file. So file name is os.path.base name, and then we can pass the file here. Actually, let's do it outside with open because the file I'm interested here, let's actually call this file path. And then file path. And let's make the source ID os.path.split text file name, and then let's get the first piece of the file name, which will be just the file name without the extension. And here in source, let's pass the source ID. So for every markdown file in this docs folder, we will open that file and create a LangChain document, passing here in the metadata the source as the file name without the extension. This source is what we will use in the response afterwards in the formatted output from OpenAI to get it to cite the sources that are used to generate that. So one common practice when indexing these documents is to split them into smaller chunks and also to overlap these chunks. This is very useful because when we're querying for related documents, usually the question can have answers that are spread across different documents, right? Not always we'll have all of the answers that the user asked in the same document. So splitting them in chunks allows us to mix and match pieces of different documents to craft a very specific response to what the user asked based on what's currently in our knowledge base. So let's create our split docs. Actually, let's first create a splitter, text splitter equals recursive character text splitter. Let's create a way smaller chunk because our files won't be that big. Let's put the chunk overlap at 20. Then we can do split docs equals text splitter dot split documents, and then pass in our document array. And then here our embedding will be widely used. So let's define it in the constructor like we did for the OpenAI client. So here we can do self.embeddings equals, and then we can instantiate this. We don't need to pass the model. This is the default model. Let's just pass the OpenAI API key and pass our API key here. Let's actually also define our vector store and start it as none. We instantiate that below here when we load the documents. Let's define self.vector store equals chroma from documents, and then we can pass our split doc, our embeddings, and then a directory where we can persist this data. Chroma by default will run locally and save the data into the storage. So here's where we define the directory where it will be saved. In previous versions of Chroma, we had to do the self.vectorstar.persist, but this is done automatically now, so we don't need to do anything like that. And we don't need to return anything, right, as well, because we are defining the vector store here. So we load the documents into this vector store and persist them to the file system. This means that this indexing phase will only need to be done once every time we add a new document, right? So if we already have our documents on the docs folder and we have already indexed them, we don't need to do this load documents every time. We just need to process this and save into the vector database when we add a new document, for instance, because that will be saved and persisted to the storage. Now let's define our structured response. Class rag response. Let's extend base model. Let's make it give us the answer in a sources list. It should be a list of strings because it can, like I said, use multiple sources to craft a response. Then let's also make it first generate a reasoning, just to try to make it a little better in the final response. Let's add a reasoning field, answer, and sources. This is our structured output. So now that we have this vector store here, the retrieve document will actually be super simple. We can just directly return self.vectorstore.similarity search and query. This similarity search function is implemented by the Langchain vector stores. Now that we got that out of the way, let's call the OpenAI API here. So we can get related documents equals self.retrieve documents and passing our query. Let's also do a print statement here for logging. So for doc related documents, let's print the source and the content and some new lines to separate it. Then let's create a prompt here. Prompt equals f-string. So here you can add, please answer the following question based on the context provided. So we can do question query and context. Let's add in our related documents. So this is the user query, and then we're enhancing it with the documents we found in the vector database, right? So here our response, we can pass the messages just the role user, and the content we can pass in our prompt. Then we can pass in a response model, regular response. But here, instead of chat completions create, we need to use beta.chatCompletions.parse because we're using a Pydantic model as the response model, and this is only supported in the beta chat right now. Maybe when you're watching this video, this is not the case anymore, but right now, response format, actually not response model, response format is requires us to use this beta version of the API SDK. And let's actually get the parsed version of our response content, print it out here, or actually instead, let's just instantiate our rag, load our documents, and then ask the same question we did on our simple rag. What are vector databases and how do they relate to rag? Here, let's print our answer, sources, and the reasoning so we can see what's behind the answer as well. And also here we won't need JSON anymore. All right, so let's create some docs real quick with that information. All right, so I created some models. I created rag with some explanation of what it is, vector databases, Langchain, padding, chroma. So these are all markdown files, and each one has some information about these topics. And the ID, basically the source IDs, will be just this file name without the .md extension. So now let's try running our advanced rag. Advanced rag.py. Okay, I forgot to install the ChromaDB, so pip install ChromaDB advanced rag.py. So it's taking a while because it's indexing our documents, but then here you can see the vector search results. So it considered all of these documents related to our query. Oh, actually, I got a problem in our parsing. All right, let's actually do it the old ancient way and import JSON here. And instead of looking at the parsed, we can have content, and response JSON equals JSON.loads, and let's return that. So now that it's already indexed it once, when we run this again, it will be a lot faster because it won't have to index all of the documents again. Now it already found the same document. Let's see what it generates. Okay, so here's my answer. Vector databases are specialized databases for storing, searching vector embeddings, enabling efficient retrieval of similar vectors using methods like approximate nearest neighbor search. They relate to RAG, Retrieval-Augmented Generation, by providing the necessary external data that RAG systems can retrieve to enhance their responses, allowing AI models to access and integrate specialized or updated information. Here it cites sources that it used, vector databases and RAG. And here is the reasoning behind the response. So congratulations again. Now you have implemented a fairly complex RAG system using a vector database. And here you can extend it however you want, right? You can add pipelines for uploading and indexing the documents and storing that into Chroma. You could create an API to interact via chat with this LLM and have it enhanced with your documents, your personal studies or whatever. So yeah, you're ready. Congratulations. You have graduated my one video RAG course. So thanks for watching this. I hope this was useful for you. Please leave any feedback that you have in the comments so I can improve the next guides and tutorials. And also feel free to suggest topics or videos you'd like to see me cover here on the channel. Thanks again for watching and see you on the next one. Bye bye.